Yeah, extend such that like I have my speaker view versus.
Yes, I think you can do that. This should be primary. Stop mirroring. Okay, this is main display. This is extend. Try.
Um, yep, yep. I'm just.
Which of your names I should use? Okay, I think
We are almost on time. We can start because I see everybody's tired. Our last talk for today is Jacob talking about data flow activity analysis with partial information.
All right, thanks, Alex. So I'm Jacob. I work on the MLIR side of Enzyme, and I'm here today to talk about work in improving the static analyses that power MLIR Enzyme. So as I'm sure we're all familiar, gradients are useful in a variety of fields, and automatic differentiation allows one to generate a program that computes the gradient of a function expressed as a computer program. Here we see one such instance. We're differentiating through an entire physics simulation of a billiards table. We can differentiate through the angle and force applied to the white ball to optimize the objective of getting the red ball as close as possible to the target blue ball. This is an inverse problem exactly as what Jesse was describing. Now, if you're differentiating something as complex as a physics engine, existing AD tools may or may not be the right fit for your use case. This is an overview of how our work compares to prior work along two axes. The x-axis here refers to the generality of input programs. Machine learning libraries like PyTorch and JAX place heavy restrictions on the input language by disallowing in-place mutation. General purpose AD systems like Tapenade allow for mutation, but assume complete access to the source code being differentiated, which might not always be the case in instances of separate compilation, custom derivatives, or multi-source AD for heterogeneous computing. Enzyme aims to relax these restrictions to be as general as possible, but Enzyme's existing activity analysis has a monolithic design that combines a number of separate responsibilities, as we'll go into more detail on, leading to a higher compiler complexity. As further motivation, the general attitude of the AD and compiler communities is that you really need whole program availability. Pointer analysis is an important prerequisite of general activity analysis, and a 2015 survey on it states exactly this. So too does a 2013 paper on Tapenade. AD systems must be global, and therefore there is no such thing as separate compilation. Now, global program analysis is very powerful, but it comes with important limitations. Modern compiled languages almost universally have incremental compilation such that when you make a small change in your program, you only need to recompile that part instead of recompiling everything. As your programs get bigger, this could mean the difference between waiting for multiple hours versus multiple seconds after the smallest change. Also, as previously mentioned, you might not have access to the source code in cases of libraries or custom derivatives. We'll use this big picture roadmap to guide the rest of the technical part of the talk, first covering the prior way of performing activity analysis that we refer to as the global analysis model, and then we'll show how we can reuse pieces of our global analysis model applied in a different way to get our partial information model. For starters, what even is activity, and why does it matter? Suppose we have an input program, and the user has requested the derivative of the first output with respect to the first input. This function computes the sine of A, adds B, and returns it as the first input, and then it has this big computation that iterates a bunch of times to compute the second return value. When we differentiate it, a naive AD tool will generate a backwards pass that goes through the program in reverse order, emitting partial derivatives for each instruction, using the chain rule to combine these partial derivatives together, and it creates this backwards loop, iterating in reverse and computing all of the partial derivatives that are emitted in the loop. However, as we know, the user only cares about the partial derivative of the first output, and so they'll call this differentiated function initializing the output derivative of the second output to 0, as our differential d value is 0. Inside of our reversed loop, dd times b and dd times c are both 0, and this entire loop consists of adding and multiplying a bunch of 0 values. We can reason about this more concretely by looking at the differential data dependency graph. The nodes here are variables, and the edges correspond to differential dependencies between the variables. So for example, if you were to slightly perturb A, there would be a non-zero perturbation in the value of C. You'll probably recall that this is the very definition of a derivative. When you perturb the input, is there some difference that appears in the output? If we statically know that there is no contribution to this output, then we don't need to compute a derivative with respect to it. This is the key idea of activity analysis. We reduce unnecessary work by statically identifying when instructions and variables don't need to be differentiated. Note that activity is a maybe active property, where it is safe but not helpful to conclude that something is active. But if we say that something is not active, we have to be certain. Otherwise, we won't generate required derivative instructions, and the results will be incorrect. Now, this is the canonical way of finding activity. If we have this nice differential data dependency graph, we do a forward traversal starting from the active input, A, and we find all of the descendants of our active inputs. Then we do a backwards traversal starting from all the active outputs and finding all of the predecessors. Any node that is visited in both traversals is marked active. Now, if your language allows mutation and arbitrary pointer aliasing, your activity analysis needs to be aware of this. In this example, we allocate some memory and produce two different pointers, pointer 1 and pointer 2, that both point to the same allocation. In other words, they alias. If we only look directly at the code, we can only see these square edges that represent memory operations. X is stored into pointer 2, and Y is loaded from pointer 1. We need some kind of analysis to reason about what these pointers point to, and this is exactly the job of our pointer analysis that will give us these circle edges that tell us that pointer 1 and pointer 2 point to the same memory allocation. It is only after we have this information that we can see the underlying differential dependency from X that flows through the memory and then to Y. To complicate matters even further, AD systems typically use whole program aliasing information. In this example, suppose we're analyzing this function foo, and we have no way of knowing the aliasing properties of Y and Z. All we see is that X is stored into whatever Y points to, and Z is loaded from to produce the return value. Do they alias? We can't know. It isn't until we look at the caller of this function that we see, there is an instance where they do alias, and thus there is a path that flows from X to the return value of foo. You might be thinking, this pointer aliasing is such a pain. I'll just disallow in-place mutation. If you do, that's great, because the differential data dependencies become very easy to follow, and you no longer need a pointer analysis to do your activity analysis. However, if you're like us and you really want to support mutation, the established way to do this is via whole program pointer analysis. This is hopefully motivated at a high level why the global analysis model is what it is. We do whole program pointer analysis followed by whole program activity analysis. Now, what if we no longer see the whole program? Things get a bit trickier. If you were analyzing this example globally, you could see there is this allocation wrapped inside of a function that is returned and then used to hold active data. But if you don't see the whole program, if we only see the custom alloc, we don't see any differential data movement. All we see is an allocation that gets returned. In this case, we have to consider that when there are allocations that escape the current function, they might be used later to hold differential data. Another source of complexity is that when we're going top-down and we don't have access to the implementation of the function, we have to make conservative assumptions about their behavior. So suppose we're analyzing the bottom, where we're analyzing caller, and we have this function call to foo. All we know about foo is the signature. It takes a pointer and returns a float. Is there a differential data dependency between foo? Well, we have no way of knowing. It is possible that maybe foo loads from the pointer and then returns it. If we were analyzing it globally, we could see that there is no actual differential data dependency, and this entire program is constant, meaning that its derivative is 0. But we have to be conservative if we are missing this global information. We're now going to zoom in and cover the two components of global pointer analysis, computing the bottom-up summaries and computing the top-down results. Function summaries are an established technique for performing global analysis. We represent a program as a function call graph where the nodes are functions and the edges between them represent function calls. So here we have a sample program where A is a function that calls B and C, and B is a function that calls D. The heart of using function summaries is that we traverse the call graph exactly twice. For simplicity, we're assuming there's no recursion, so there's no cycles in the call graph. The principle still works. It's just a bit more involved. You have to go iteratively. Assuming there's no recursion, you go bottom up, starting from the leaves of the call graph, and you propagate summaries. You compute summaries which describe the relative effects of what this function does, and you pass this up the call graph. The summaries are used at the direct parents. So B, to compute its summary, uses a summary of D. The summary will describe the relative effects, and then we go top down, starting from the root of the call graph, to convert the summaries to actual information. This is probably very abstract, so we'll take a look at making this more concrete in the example of pointer analysis. The following program consists of 3 functions with the following call graph. Caller calls boo, bar, and foo. Starting from the bottom, we have this initial state for bar. We have a pointer argument, my pointer, and we have no idea what it points to, but presumably it points to something. Even though we don't know what it points to, by just looking at the body of bar, we see that the return value of bar points to the same placeholder, even without knowing what that placeholder is. Then we visit foo. The initial state, we have 2 pointers, presumably they point to something. Again, we don't know what they are. And we look at the function body of foo and see that nothing changes. There aren't any pointers being stored into here. The return value isn't a pointer. So the final summary of foo is the same as the initial state. Finally, we look at caller. The initial value of the summary is empty here because none of the arguments are pointers. However, when we analyze caller, we now have this concrete allocation. We call it B malloc, and we know that B is a pointer that points to our allocation. Additionally, we can use the summary of bar because bar is called with B as an argument, and the summary of bar tells us that the return value of this argument points to the same memory allocation. We fill in the placeholder from before to conclude that C points to B malloc. We then go top down, and the purpose of the top-down traversal is to replace all of these placeholder allocations with actual allocations. And we can see that all of these pointer values from our summaries concretely points to this allocation B malloc. And this is how we do a global analysis such that all of the pointers have concrete allocations that we know what they point to. Now we will see how activity analysis builds on this global analysis. Using the same example, we start bottom up. Starting from bar, we start with the global information that my pointer and the return value of bar both points to B malloc. There is no differential data movement, so the activity analysis doesn't add anything new. Now we look at foo, and we can concretely see that the pointers y and z points to this B malloc allocation. This is sufficient now that we see that x is stored into what y points to, which is this B malloc allocation, and z is loaded from, so we add this differential dependency from B malloc to the return value of foo. Now looking at caller, we start again from our global pointer information, and we use the summary of foo. Foo is invoked with A, B, and C, and looking at the summary, we can conclude that there is this differential path from A that flows through B malloc and then flows to the return value of caller. And that is what we know from applying the summary of foo. Now, from our top-down results, we can see at the top level which variables the user cares about with respect to their inputs and their outputs. And we can see that A is active, and this top-down traversal will find this complete differential dependency path from A to X. X is stored to B malloc is loaded from to get the return of foo, and that is passed the return of caller. And this is our final activity result. Note that in the bottom-up phase, when we were analyzing foo, we're just constructing parts of the differential dependency graph. We don't know if X is active or not. With all of this background out of the way, we are finally ready to talk about how we reuse parts of the global analysis model to achieve our interleaved relative analysis that works with partial information. The key idea is that our model reuses the summaries from the global analysis model, but keeps everything relative. The relative activity summaries are computed on top of the relative pointer summaries instead of concrete pointer information. This allows us to go one function at a time, computing the pointer summary and then the activity summary, rather than waiting for all of the pointer analysis to be done before we start activity analysis. There is no top-down pointer analysis in our approach. The top-down activity phase is also slightly different, which we will get to in a second. We'll show this method in action using the same example. Analyzing bar, we compute its relative pointer summary using a placeholder instead of the concrete allocation, and again, there's no differential data movement, so the activity summary doesn't change anything. Looking at foo, we don't know if y and z alias, and we don't know what they point to, but we directly use these placeholder allocations. X flows into the placeholder for y, and the placeholder for z is loaded from to produce the return value. Even though we don't know what the placeholders are, we're done. Now, looking at caller, we can use the pointer summary for bar as before to conclude that C points to the allocation bmalloc. Now the fun part is applying the relative summary for foo. It is at this call site where we see that foo is called such that x equals a, y equals b, and z equals c. And this tells us that a is stored into what y points to, which is bmalloc, and the return value is loaded from what z points to, which concretely at this call site is again bmalloc. Here we're directly comparing the summaries achieved with global pointer information with the summaries achieved by just relative pointer information. The purely relative pointer summaries still have these placeholder allocations because there's no top-down pointer information, but we're able to refine the information at the summaries using the summaries at the call sites. Notice that in this case, the summaries at caller that we achieve through the two methods are the same. The last piece is the seeded top-down activity analysis. We pass summaries up the call graph, but the summaries construct the differential dependency graph. When we're working relatively, we don't know the top-level active inputs and outputs. So one way to enable true separate compilation is to have multiple enzyme autodiff calls at the top-level boundaries of compilation units. If provided, we know what the active inputs and outputs are locally, so we no longer need a fully global top-level activity analysis. Now, briefly revisiting the extra case that partial information introduces, our pointer summaries give us an easy way to determine when allocations escape our view. If we're at the top-level boundary of a compilation unit, and we see that from the pointer summary, either the return of an argument or an argument summary transitively points to a fresh allocation, then we conservatively mark this allocation as active because it might be used in an active way outside of what we can currently see. The entire talk until now has been comparing the partial information model against the global information model. We'll now briefly discuss the other axis, this y-axis, to compare against Enzyme's existing activity analysis. Enzyme's existing analysis, which we're calling Enzyme 1.0, jointly tackles pointer, activity, and escape analysis in this coupled way, which results in a combined analysis that needs to juggle a lot of responsibilities at once. In contrast, our work cleanly separates the analysis into simple, modular pieces that each have a defined responsibility. I didn't have time to fully go into detail about all of the details of the data flow model, but it gives us a number of theoretical benefits in addition. The first one is that we have an almost trivial proof of termination, which I'm happy to go into detail about offline, which is something that Enzyme 1.0 doesn't have. We also have a precise notion of what a correct data flow solution is. This is outside the scope of the talk, but part of the ongoing work is to demonstrate that the correct data flow solution is indeed a correct activity solution. To empirically evaluate our approach, we implemented both the global analysis and the partial information models in the MLIR data flow framework. We took a collection of benchmarks written in C and C++, lowered them into LLVM-IR, translated them to the LLVM dialect of MLIR. We ran our analyses, exported them into annotated LLVM-IR, and then we differentiated and then evaluated the precision of our results. To do so, we looked at the percentage of LLVM instructions in each benchmark that each analysis was able to prove not active. This is a proxy for performance because the more instructions you prove not active, the less work your AD system has to do. Our evaluation has two baselines, Enzyme 1.0 and global analysis. We can see that while global analysis is occasionally a bit more precise than Enzyme 1.0, they're usually neck and neck. What's more interesting is that in every case, the partial info analysis is exactly as precise as the complete global analysis. This demonstrates that we can get just as good activity information in a separate compilation environment if we only share the function summaries and the seed activities. So, to reiterate, this work shows that activity analysis can be performed in a separate fashion by sharing summaries and seed activities. The summaries are propagated bottom up, while the seed activities are propagated top down. Additionally, users can provide summaries for libraries where they don't have source code to get as precise results as if they had the source code. There are a number of avenues for future work. Currently, the pointer analysis, and thus the activity analysis, is field insensitive. If one member of a struct is active, or if one element of an array is active, then the entire struct or array is also considered active. We can potentially improve the precision by tracking separate activities for each struct member or each array element, if that is useful. In addition, the summaries right now are essentially a serialization of the entire relative analysis state. It might be possible to simplify the summaries and simplify the information that we pass between compilation units without losing too much precision in the results. Finally, I'm personally interested in how this work will impact the other analyses of Enzyme. Differential use analysis affects the memory overhead of reverse mode AD, and it depends on activity analysis in the same way that activity analysis depends on pointer analysis. Type analysis remains a significant compile time bottleneck, and it remains a question if it can be expressed using this interwoven partial information model. Finally, we mainly looked at activity in improving run times, but it can potentially also improve compile times as well. If, for example, you have a memory allocation that is proven not active, then we don't need to run type analysis on it because it doesn't matter what type it is. We're not differentiating it. That's it for my talk. Thanks for listening.
Maybe Jacob, any questions?
So you have some notion of separate compilation,
Yes.
right? I'm wondering, I guess maybe general question is, do you have a notion of semantics here? Like, do you have a formal semantics? And then if either way, how do you formalize separate compilation?
That's a great question, and I think my best answer right now is no. We don't have a way, to my knowledge, of formalizing separate compilation, but it sounds like something that we need to do.
I would love to talk about this.
Great.
Yeah.
That's why it has a hackathon. There was a question behind.
Yeah. So you mentioned about Enzyme 1.0 not having a termination to file. Can you say a bit more about that? What is that, like, termination for a specific expression?
Can you repeat the question also?
Sure. So the question is that we mentioned Enzyme 1.0 doesn't have a proof of termination while our approach does. Specifically, what this means is that there are cases when you run program analysis that you get into an infinite loop and the analysis never terminates. The compiler just goes on forever. And Enzyme 1.0 has a bit of a barrier to entry and understanding, and so there isn't a theoretical justification that it will always terminate. We kind of don't know. In practice, so far I think it has always terminated, but we don't have the theoretical background that really can speak more on this.
really wants to comment.
I'm going to comment in this very slightly. It does have a theoretical basis for terminating, but not necessarily with the best asymptotic guarantees. Specifically, activity analysis and also type analysis has a finite state space, and thus you can only visit it X many times. Becoming a finite state space does not necessarily mean that it has the correct asymptotic number of things inside of it, which is particularly why we started looking into, can we theoretically both improve the practical as well as guarantee properties of these analyses, which is why we did this.
Yes.
Just to summarize, does that mean less segmentation for?
No.
Unfortunately, that is an independent problem that we're also interested in.
Jan had a question first.
Okay. So I'm sure you're familiar with the tapenat also generates sort of summaries for each function, right?
Yes.
And then does analysis based on that. And one observation that I always had was, I mean, it doesn't cache them, right? I mean, it would be great if it could somehow not revisit everything next time you do it. But also, if you change a function that lives very deep down in the call tree, you will change its summary.
Yes.
But then as a result, you will change the summary of everyone who uses it, who uses that, and so on. So you still have global effects, right? You don't have the nice property that you just change this small library, C code, recompile that, everything just works. Did you get around that? Because, I mean, the summaries still change, right? So you could still potentially invalidate everything by just changing the implementation of some tiny function that lives in a different translation unit. Or am I misunderstanding what you do? You still have that problem, right? You're just not revisiting all these source codes again.
Currently, yes.
Yes.
Yeah, that does accurately describe a limitation. I would be really interested, because part of this goal of separating out the compilation, one of the claims that I would like to make but is currently unvalidated is that if we have activity information from the top level, we no longer need aliasing information. So, for instance, when we seed the activity and we're analyzing just foo, we know that y and z are 2 pointers that are both active. One of the things that in my mind is that I think it doesn't actually matter if y and z alias or not, because the reason that their aliasing does matter is because if they do alias, then the activity depends on each other. But if we already have the activity, we don't need that. I think there is a similar argument to be made about if we can determine that information doesn't matter, even though we don't have it, when going the other direction.
An activity analysis on the activity.
Second order activity.
Yeah.
So you could optimize the global nature of the problem away in some cases, but it's still fundamentally a global optimization that you're doing, right? With sort of clever caching sprinkled in, I suppose. But
In the worst case, yes. I think that's accurate.
Yeah.
I think one thing that I might follow up is sort of like, it's sort of what I understood you referring to is more sort of like, an incremental sort of change here, where like, imagine, your Julia, right, where you have like a JIT function that updated the definition of. There's a separate, really interesting question now asking whether or not, we can not have to go through all the rest of the sort of program state and see if we can only update the minimal piece. This work isn't really as much exploring the incremental component, which would also be interesting to do, to be clear, but more so the point of like, can we, factor the problem of activity into these separate pieces and then sort of combine them where we don't need to look through all of them at once. It still doesn't, it still needs to, you obviously need to have each part impacted by these other pieces, but we don't need to look at them all in their entirety.
Makes sense.
Valentin, you had a question?
Yeah, how tightly is it coupled to the MLIR data flow analysis? Could we get this into non-MLIR based enzyme?
We would need to re-implement a data flow framework for LLVM, and if we did this naively, we'd have 2 independent implementations. But I don't think that there is anything that is radically special about the MLIR data flow framework.
So what it's worth, I think LLVM would be simpler.
Yes. Yeah, so I think that's definitely possible.
Yeah, I've been considering whether or not we need to implement activity analysis over the higher level Julia IR before we go to enzyme. We could do this very similar analysis on just the arguments and outputs, and then if we precede the local activity analysis with that information, we could do decoupled compilation.
Did you know just convert your Julia IR into MLIR? And back.
You work at Google, right? You can make that happen.
There was a question over there. You had it.
So maybe another question. So I think I only see the tags, like tag 0.098. I do not see 1.0. Is there a special version of the next 1.0?
Oh, okay. Yeah, that's my bad.
Repeat the question.
So the question is, in this talk, I called it Enzyme 1.0. Enzyme itself doesn't have a 1.0. That's totally my bad and a poor naming choice on my part.
No, it's a Google way where, if you don't know, the Google way is we have two versions. One is deprecated and the second one is not ready yet. Same here, same applies.
Yes, and I meant Enzyme 1.0 specifically the activity analysis, because in evaluating the rest of everything, although the results weren't shown, we plug in the different activity analysis, but everything else is the same infrastructure as what the current enzyme is. The actual generation, all of that is the same. It's just a naming choice for just the activity analysis.
So that one has not been merged into, your development has not been merged into the repository?
That is correct in that if you're using enzyme proper on LLVM, you won't use this.
To perhaps give a little bit of extra clarity here. So enzyme has activity implemented inside of LLVM. It's had it implemented since very early on, and it continues to have a version of it implemented to the latest commit as of right now. Jacob has an activity analysis also in the enzyme repo, but which is not the default when you use the LLVM version of enzyme. It's also actually the default if you use the MLIR version of enzyme, but you can use it if you want. Jacob's distinction here is referring to, quote, enzyme 1.0 as the default activity analysis in enzyme presently that also just doesn't have a better name, which we should probably give it a better name, as distinct from his new implementation of activity analysis using Dataflow, which at one point, hopefully that gets merged into become a default to resolve the previously alluded to issues with the earlier one, but the tag, at one point, we should actually, ironically, we're in the process right now of making the C++ interface a little bit better, throwing better error messages, and eventually release a formally named 1.0 as opposed to a bunch of patch bump versions. But yeah, the 1.0 being referred to by Jacob right now is just referring to the default current activity analysis as opposed to his new implementation of activity analysis, which is also still in the enzyme repo, but just not the default. Yeah.
Okay.
Is it like a drop-in replacement? Can we use this activity analysis just to see if our programs perform better or compile better?
If you use MLIR, it is a drop-in replacement. If you use LLVM, it's a little bit more tricky to set up.
You got to do this.
Yeah.
Where you emit LLVM, raise it, run the analysis, convert it back down. It's more involved.
Which doesn't mean we shouldn't make it easy and a option which you can switch to, but you got to start somewhere. You got to implement it, see the theoretical pieces, and then make it easy.
So when I compile my program, it's usually the link time optimization. At that time, it generates a gradient.
When you apply enzyme, be it at regular compile time, link time optimization, JIT in the case of Julia, is independent of which of the activity analysis you use. Just that is sort of, you're running enzyme, and inside of it has all the analyses and code generation. It's during that phase, which doesn't matter how you were calling it, that you would want to change it to now go to the currently implemented MLIR Dataflow activity analysis instead of the default one presently.
Okay, we are out of time. I think that's a great way to continue as a leftover hackathon. I think we have room for 2 more hours, so we have plenty of time for discussion. Thanks everyone for coming today. We'll restart tomorrow at 10 a.m. So it's not very early, it's on purpose, but please be here if you can. Thank you, Jacob. Thank you very much.